there is a last topic that I would like to review with you at the conclusion of this review of atom-light interaction. And this topic is the representation of the dynamics of a two-level system in terms of a Bloch vector and the Bloch sphere. So this is something that you have already studied, so I would like only to recall the definitions to show you then some relevant examples. And so what is a Bloch vector? The Bloch vector is a three-dimensional vector that is composed starting from the components of a density matrix. And in particular, this Bloch vector that we will denote as R, and we will denote the three components as U, V, and W, is defined in this way. So the U component is given by rho E G, and we are considering the rotating wave approximation components of the density matrix, so rho E G tilde plus rho G tilde. So the E component, so the V component is I times rho E G tilde minus rho G E tilde, while W is the rho EE minus rho GG tilde. So these are the three components of a Bloch vector. These can be rewritten also in this way. So the first component is 2 times the real part of a coherence rho EG. So the second part is minus 2 times the imaginary part of a coherence rho EG tilde, while the third component is the population difference that we denoted as delta rho. So the Bloch vector basically is a complete description of the density matrix for a two-level system, since it contains the information on the diagonal components, since we have the additional constraint that the trace of a density matrix has to be equal to 1, so the diagonal elements are completely determined by the third component of the Bloch vector, while the two coherences, the two of diagonal components, are given by the first two components of a Bloch vector, U and V. And so what are the properties of this vector? First, so its modulus, in particular, so its modulus square, it can be shown with some algebraic passages and exploiting the properties of a density matrix, that these can be written as 2 times the trace of a square of a density matrix, minus 1. So now, from this expression, we can derive an interesting result, because we already know the connection between the trace of rho square and the pureness of a quantum state. So in particular, we know that if the trace of rho square is equal to 1, this means that the modulus of a Bloch vector is equal to 1. So this corresponds to a pure quantum state. So trace rho square equal 1, while for a mixed state for which the trace is smaller than 1, the modulus of a Bloch vector is less than 1. So what does this mean? This means the following. So let us now introduce the representation of a so-called Bloch sphere. So forgive me for the drawing. So the Bloch sphere is a sphere in which you have U and V plotted on the horizontal plane, and W instead plotted along the vertical line. And so the Bloch sphere is a sphere of radius 1 that is located at the origin of this reference frame. And so if you have a pure state is described by a Bloch vector that lies on the surface of the Bloch sphere, while if you have a mixed state, the mixed state generally will point to an arbitrary point inside the sphere. So I'll say it again. So if the Bloch vector has modulus 1, so the Bloch vector lies on the surface of a sphere, and this describes a pure quantum state. Differently, if you have a mixed state, the Bloch vector will have a length that is smaller than 1, and so it will point inside the sphere. And so, representing a quantum dynamics on the Bloch sphere is particularly useful to understand what happens in a two-level system, even without carrying out the calculations. Why it is like that? Because we can rewrite the Bloch equations, so the optical Bloch equations we introduced in the last lecture, in terms of the components of the Bloch vector. So this is rather simple. So I don't make the full calculation, but basically it's just some algebra. So you take the optical Bloch equations that are equations for the coherencies and populations of the density matrix, and you perform a change of variable that is given by the definition of the elements of a Bloch vector. And so, as a consequence, you have some equations for u, v, and w. And so I will write them. And so u time derivative is delta v minus gamma half u. V dot is minus delta u minus omega w minus gamma half u, v. And then w dot is omega v minus gamma times w plus 1. So these are the same optical Bloch equations that we have already studied that are recasted here in terms of components of a Bloch vector. And why is it interesting to rewrite them in this way? Because of the following. So if we neglect for a moment the gamma terms, so it is easy to show the following, that the time derivative of a r vector so can be written as the cross product of a vector omega times the r vector itself, where the omega vector, also called the Rabi vector, is defined in this way as omega 0 minus delta. So the Rabi vector contains information on the light-atom interaction. The Bloch vector contains information on the state of a two-level system. And so combining these two vectors together, you find this quite simple equation of motion for the Bloch vector that basically this is nothing but something that you know very well also from dynamics and from mechanics and from electrodynamics. For instance, this equation is basically a precession motion. For example, the precession motion that you have for a magnetic dipole moment around a magnetic field. So you know that the dipole moment will perform a precession motion in which the vector will rotate around the vector of a magnetic field. Or you have some similar examples in mechanics when you have precession of angular momentum and so on. So this is a kind of very simple equation, and so I will try now to give in the rest of this video some examples of these dynamics. Let me just tell you for completeness that if you have now some spontaneous emission, so this equation will be complicated a little bit. So you will have to add the gamma term, and the gamma term is a kind of damping term that can be written in this way as gamma multiplying a vector u half, v half, and w plus 1. And this is the full equation that drives the dynamics of the Bloch vector. Okay, so I'd like now to give you some examples of dynamics on the Bloch sphere. So let's start with something that we already know. And for showing you these examples, I have prepared a Mathematica file that I will also give you, and I will put it on Moodle, so if you are interested, but just if you want to play with parameters, so if you are curious about looking at some dynamics, you can use as you want. And if you have problems, just ask me, and I will give you some information. So this is the file. So we have some definitions here, but now let me just show you some examples. So first, let's look at some Rabi dynamics. So some Rabi flopping on resonance. So here we have some values for the Rabi frequency, and we have 0 decay, so 0 spontaneous emission and 0 detuning. So coupling on resonant with no relaxation. So we expect to observe some perfect Rabi oscillations with an amplitude of excited state population from 0 to 1, and this is what you will see here in this figure. So let me see if I can make the screen a little bigger. Yes, it should fit. Okay. So at left you will see the animation on the Bloch sphere. On the right you will see the excited state population. So basically the same plots that we did in the previous part. So let me play it. And so what you see here is basically the same Rabi flopping dynamics. So the Rabi flopping dynamics, so what we are plotting here is the population of excited state. So this is basically related to the projection of Bloch vector along the vertical axis of the Bloch sphere. So this dynamics on the Bloch sphere is basically a rotation of a Bloch vector around the direction of the Rabi vector that is along the u direction. So if we take the definitions we considered before, and let me do it. So in the case of resonant interaction, the Rabi vector you can see here as delta equals 0, and so the Rabi vector is pointing only along the u direction. So this Rabi vector is pointing along the u direction, and you can see here quite clearly that the state vector that initially is pointing downwards. So I haven't said that, but I will say it now. So on the Bloch sphere, so the south pole corresponds to the ground state G, while the north pole corresponds to state E. So all the other points on the Bloch surface corresponds to a different superposition of G and E, and in particular, the points on the equator of the Bloch sphere corresponds to points of equal weight of superposition of G and E. So, if you have a Rabi oscillation between G and E, this is basically a circle that is happening on a meridian of a Bloch sphere. So, in this resonant case, the Bloch vector is the Rabi vector is along U, and you have this precession of the state vector along the direction of U, around the direction of U, and the Rabi oscillation is related to the projection of this Bloch vector along direction W. Okay, now let's put some detuning, for example. If I put some detuning, so now we still have 0 relaxation, but a finite detuning. So this is a Rabi flopping out of resonance. Let's look at the dynamics now. So out of resonance now means that the Rabi vector has acquired some component along direction W. So it is not pointing in direction U, but it's pointing in a plane in a plane identified by u and w. So in particular for a positive delta, so this is pointing downwards. So as you can see here now, the Bloch vector is pointing at an angle, and the Rabi oscillation will be again described by a precession motion of the Bloch vector around the Rabi vector, similar to before, but now, of course, the angle between the Rabi vector and the Bloch vector will be smaller, and so as a consequence you have a Bloch oscillation that happens not on a meridian of the Bloch sphere, and so the maximum height, so the maximum latitude that is reached by the Bloch vector is lower than 1, and so you have this Bloch oscillation that reaches a lower amplitude. So we can do other examples, and for instance, this is the case of even higher detuning. So delta is much larger than omega, so we expect the Rabi flopping to have a very small amplitude. And so this is what we can see now. So as you can see, the red vector is pointing more to the south pole, so the angle of the Rabi vector with a Bloch vector will be smaller, and so the precession angle will be smaller, and as a consequence, the amplitude of the Rabi flopping will be reduced. In this particular example, so the maximum amplitude of oscillation will be lower than 1/2. Last simple example, so this is something that we already have studied, but the visualization on the Bloch sphere, I find it always particularly interesting. Now let's consider the case with relaxation, so with spontaneous emission. So this is the case of a gamma value that is different from 0. So we are on resonance. So now the Rabi vector will point again along direction u, but differently from before, we will have some relaxation. And so, and the effect of this relaxation, you see here quite clearly that so the system changes from a pure state at time t equals 0 to a mixed state to a time larger than 0. So you see here quite clearly that the arrow of the Bloch vector reduces in modulus. So the modulus of r is less than 1, so this arrow will not point on the surface of a sphere, but in the interior of a sphere. And so the result is the damped dynamics that we have also studied before, that now is plotted on the Bloch sphere. Okay, so one can study many different examples, but this is something that we have already studied. So now I would like to show you a different example. So this example is what we call adiabatic passage. So what is adiabatic passage? So the problem is the following. Let's suppose that you have a two-level system that is initially in the ground state G, and suppose we want to excite it to the excited state E. And suppose that you want to do it in the most precise way you can. So the idea here is just to apply some field in order to make the transition from G to E and then stop this field in such a way that the system stays in the final state. So we want basically in the two-level description to start from G and taking advantage of a coupling with radiation, so bring the atom from G to E and leave the atom in state E. Suppose that we don't have any relaxation now. So suppose that E is stable, and so that we don't have this additional term in the evolution equation for the Bloch vector. So there is already one method that you know. One possibility to do that is drive Rabi oscillations, of course. One could drive Rabi oscillations and stop the oscillation at the time of a pi pulse. So remember the pi pulse we have reviewed in the previous part. So at a pi pulse, so the duration of the light atom interaction is the right one to create an inversion of population from G to E. However, this pi pulse is subject to, for example, some experimental uncertainties. For example, if the Rabi frequency changes because your laser power is changing, or because, for example, you could have possibly some fluctuations in the detuning or in the resonance frequency or in the frequency of your lasers, so this pulse could not be as ideal as in the ideal case. So there is another method to drive the population from the ground state to the excited state. This method is called adiabatic passage. And so what is the idea of the adiabatic passage method? So in this method, basically, you are changing in time the detuning of your radiation. So as a function of time, your delta will change. For example, this changes because you are changing the frequency of your laser. So you're changing that from values which are higher than the resonance frequency to values that are lower than the resonance frequency. So with a kind of dependence like this. So it has not to be linear necessarily, but I've just plotted here as a straight line just for as an example. So the important point is that it should start from a positive value and it should end at a negative value, and it should cross the resonance at some point. We call it adiabatic because in the ideal case we want this passage, this change in the parameters, to happen at a very long time, in particular much longer than the Rabi frequency, than the inverse of Rabi frequency. Okay, so and why one does this trick? So if you do that, so the final state, so suppose that you start with the atom in the G state, you end up with the atom in the E state. So one could make the full calculation, but it is not necessary to understand the physics. Why? The Bloch description is enough. In particular, we know the evolution of the Bloch vector in terms of precession around the Rabi vector. And so if you do this kind of frequency sweep, what do you get? So in the in the Bloch sphere, so very large delta, so means that omega vector initially, so the omega vector is defined in this way. So basically, if delta, the initial delta, is much larger than omega, so this, let's call it delta 0, is much larger than omega, so this omega vector will point initially downwards to the south pole of the Bloch sphere. Then, so this is what happens at, let's put some labels here, at time A, this is time B, this is time C. So at time A, this is the Rabi vector. At time B, the detuning is 0. So at time B, the Rabi vector will point along the equator of a Bloch sphere, while at point C, the Bloch vector will point at the north pole of a Bloch sphere. So during time, the Rabi vector is performing a rotation around the Bloch sphere. And so you know now that Bloch vector, so the state vector, should precess along this changing direction of the Rabi vector. So now let's take the Mathematica notebook. So adiabatic passage. So there are some parameters here, and these parameters are chosen in such a way that the process is working. So these are good parameters, and I'll show you the result of that. So as you can see here, at the beginning the atom is in the G state, so the blue vector is pointing at the south pole, but also the Rabi vector, so the red vector is pointing at the south pole. And so at the beginning you have a very tiny precession of a blue vector around the red vector, but then as time changes, it's the Bloch vector that precesses along the changing direction of the Rabi vector, forming always a very small angle, so the process is adiabatic. So basically the blue vector follows the change in orientation of the red vector. So at the end you can see here that with very small residual oscillation, so the state of a system changes from the G state initially to the E state finally. And so this is a kind of very robust protocol, because if, for example, the power of your laser is changing, is fluctuating, or the frequency is fluctuating, this is working because you start from very large detuning, you end with a very large detuning. At some point you will cross the resonance, and if you cross the resonance slowly enough, so the red vector will move slowly enough, the blue vector is able to follow in an adiabatic way and to drive the system from the ground to the excited state. This is the adiabatic passage. Of course, if you're not careful with the choice of the parameters, so this process can be non-adiabatic. So this happens, and you can see here, if the time, for example, chosen for the process is not large enough. So instead of having this sweep on a time scale of 50 time units, now the same process happens in 2 time units. So this sweep is made in a smaller time. And so the result is the following, and it will be remarkably different from what we have seen now. So if this sweep is fast, compared to the precession period, you can see here that basically the Bloch vector changes loses the alignment with Rabi vector, and so basically you have a final state that is very out of equilibrium, in which you will keep the system will keep rotating as crazy along the final direction of the Rabi vector, and the final state is very different from the state at the North Pole, which was the target state for our protocol. So this kind of idea of adiabatic passage, it is interesting because first, it is one example in which the dynamics on the Bloch sphere is useful to understand the physics without making any explicit calculation. Second, it is important for many protocols of quantum information processing when you use atoms to store quantum information in the atomic qubit. Third, these dynamics from the adiabatic dynamics to the non-adiabatic case will be very important when we will speak about magnetic trapping of atoms in probably 3 or 4 weeks from now, and I will, in a completely different situation, I will consider again this kind of dynamics on the Bloch sphere. So keep this in mind. So let me discuss now a last example of dynamics on the Bloch sphere. Again, this is interesting by itself, but also for what we will study, especially in the last part of the course when we will deal with atomic clocks. So one famous spectroscopic technique that usually is employed in the context of microwave spectroscopy, but it also is important in the optical domain, is called Ramsey spectroscopy. So let me show you what we mean by Ramsey spectroscopy. So what you see here in the top of this slide, so in the A case, is an experiment, is a spectroscopy experiment made with an atomic beam. So this is a kind of a pretty common configuration in traditional atomic clock experiments, like the experiments that allow a definition of a unit of time of a second. Here you have a flux of atoms coming out of an oven, and these atoms then are selected to be in just one particular state. So here, instead of using GE notation, I've used 1 and 2 notation, but the physics is the same, of course. So let's suppose that 1 is the ground state. So you have atoms in the ground state that travel and pass through this region. This region is a microwave cavity, so atoms can be excited from state 1 to state 2 only when they travel in this cavity. And then there is some setup after the passage through this cavity that is used to detect by some, for example, deflection of the atoms in the excited state. This setup is used to detect the probability of excitation to the 2 state. And so if you plot it as a function of the tuning, you find some line shape, and this line shape is, of course, has a maximum for zero detuning when you are on resonance with your microwave, and so you can excite resonantly the transition in the two-level system. And so here we are considering the case of a finite interaction time. So the atoms are traveling in the microwave cavity. So depending on their velocity, there will be some finite interaction time delta t. And so if one chooses the power of a microwave in such a way that a pi half pulse is realized during this time, so this will be the resulting line shape. And in particular, the width of this line profile is given by the time. And so this is a kind of general result for spectroscopy if you have a finite interrogation time. So because of very general argument in physics, and that is based on the properties of a Fourier transform, basically, ultimately. So there is an indetermination, uncertainty between a certainty principle between time and energy, or time and frequency. So you cannot measure something. So, for example, a frequency with a precision that is higher than the inverse of a time that you have available for your interrogation. So the width of this line profile is on the order of 1 over delta t. And so for many reasons, for example, for atomic clocks experiments, so you want this precision to be the highest as possible, so this would mean to have an interrogation time that is longer. But of course, for practical reasons, it is not possible to increase this time in an arbitrary way. For example, because it is difficult to make homogeneous microwave cavities that are longer. And so this delta t is limited by practical details. So we'll say something more when we'll talk about clocks. So now, what is the Ramsey scheme? In the Ramsey scheme, instead of having just one excitation, one has two different excitations. So this is the plot. This is the scheme and the plot in the B section of this slide. So in the Ramsey spectroscopy, instead of realizing one long cavity that would ensure a long interrogation time, one probes the atoms in two positions with two short cavities that are separated by some distance, and so some travel time of the atoms that are in the atomic beam. So the atoms first will cross the first cavity. So we have a first pi half pulse by the first cavity. Then we have some time in which the atoms do not interact with the field. And then we have a second pi half pulse in a second microwave cavity that is driven by the same microwave source that was driving the first cavity. So basically, you have a first pi pulse excitation, then nothing, then a second pi pulse excitation at the same frequency. So what is the result? So if, again, we now detect the probability of excitation to the excited state, we will find the signal in this graph. And so you see here that the structure of this signal is quite complex. So more or less, so it is reminiscent of the excitation from the single pulse, in the sense that there is an envelope that resembles the envelope of a single pulse, as you can see here. So with a width that is given by the transit time in the single excitation region, delta t, but you see here that this spectrum features some fringes, and these fringes are much thinner, so the spacing is much less, and in particular the spacing between the fringes is proportional, inversely proportional to the time between the first and the second excitation. And this time can be made even much longer than delta t, and so this means that you have a very fine structure of fringes. These are the so-called Ramsey fringes within the envelope of a single pulse excitation. So we will understand why this happens in a moment, and just let me tell you that, of course, this Ramsey scheme has been very successful because if you have these fringes, it is much more easy to identify the center of resonance, because this spectrum is much narrower, so these features are more sharp, so sharper, and so it's easier to detect the resonance center. So for spectroscopy, this is a very good technique. But now, why is this happening? So what happens here? So the atoms are excited with a pi-half pulse at the first place. Then they will travel, and you have a second pi-half pulse. But the outcome of this second pi-half pulse depends on what happens in the central region, because if this was not the case, why should you observe some dependence on the spectrum on the time between pulses? So there is something happening in the dark time between the first and the second pulse. So what is happening here? So what happens is basically an effect of coherence. So Ramsey spectroscopy is a spectroscopic protocol in which you exploit the coherence between the atom, and in particular the coherence in the atomic superposition between ground and excited state, and the coherence of radiation field. So this mutual coherence between the radiation field and the atomic superposition is essential to understand the Ramsey scheme. So let me now just give you some argument just by drawing something, and then I will show you the example on the Bloch sphere simulated with a Mathematica notebook without making any calculation, just because I want you to give you the physics and not the full details, and also to show you again the power of a Bloch sphere approach to understand the dynamics of a quantum system. Okay, so first interpretation of a Ramsey process. So if you are on resonance, delta is equal to 0, what happens? So the atoms are initially in the ground state, G. Then, after the first pi-half pulse, this pulse will produce a superposition of ground and excited state. So this superposition will be 1 over square root of 2 G minus IE. We have reviewed that in the previous part. So now, what you might expect is that the second pi-half will complete the effect of a first pi-half pulse, and this is true if delta is equal to 0, and so at the end you have your final state, that is the excited state. So that is minus IE. And this is what we have studied previously. This is okay if you have zero detuning. But what happens if you have a non-zero detuning? So I will not be extremely formal here, just want to give you the feeling. Then I will be more formal in a couple of minutes. So what happens if delta is different from 0? So, again, the first pi half pulse will produce this superposition. Fine. Then, what I have not taken into account before, but it is important to take into account, is the fact that you have a free evolution of atomic superposition during the dead time. So during the dead time, let's call it capital T here, the time between pulses. So, of course, the atom does not interact with a field, because this is the dark time, but the superposition will evolve in time. So, G and E have different energies, and so the time evolution, the free time evolution of this state, apart from a global phase factor that I can neglect, will be given by the phase factor that is the free evolution for an eigenstate of two-level system. So the E state, so again, let me recall that we are dealing with two quantum states with an energy difference that is h bar omega 0. So if we take as 0 the energy of a ground state and h bar omega 0 the energy of excited state, so the excited state will evolve in time according to a phase factor that will be e to the minus omega 0 time, so capital T times E. So during time, so the phase of excited state contribution in the atomic superposition will be different. So we will have a running phase, omega 0. Now, during this time, also the field will evolve. The phase of a field, of electromagnetic field, will evolve, of course, as for example, let's consider the term which rotates in the same direction. So this minus I omega times T. So this is, let me write in a better way. So this is the electric field at time capital T. That will be the electric field at time 0 times e to the minus I omega capital T. So both the field and the atomic superposition will evolve in time. So, but while in the first case they evolved in time at the same speed, because delta equals 0 means that omega is equal to omega 0, and so basically now the rotation will be in phase at all times. So basically the phase of a field will be always equal to the phase of a superposition during the dead time. And so basically after this dead time, nothing happened. So the atom and the laser will be with the same phase again. And so the second pi half pulse will complete the effect of the first pi half pulse, as if there was no dead time in the middle. Now, when delta is different from 0, now we have a different situation, because now omega is different from omega 0, and so after time capital T, the phase of a superposition will be different from the phase of a field. And now, since the Rabi dynamics is crucially dependent on a phase relation between the field and the coherent superposition of G and E, so this means that the effect of a second pi half pulse could be different and possibly lead to a destructive interference with respect to the first pi half pulse. So, this can be seen quite clearly on the Bloch sphere in this way. So during the pi half process, so the Rabi vector is omega 0 minus delta. And provided that omega is large enough, so basically we can neglect the value of delta. So this is the regime of very strong excitation. And so this will produce this kind of evolution. So on the Bloch sphere, so let me show the other way. So if this is direction u, this direction w, so omega is pointing this way, and so in the pi half pulse, so the Bloch vector will evolve from this position to this position. Okay, so this is the first pi half pulse which creates the superposition between G and E. Then, during the dead time, capital T, what happens? So the field is switched off. So omega is 0. But still there is a detuning. So if you're not comfortable with that, just suppose to have a finite omega, but infinitesimal. So some infinitesimal value of omega. So that means that the field is there, but with a infinitesimal amplitude. And so what is important now is just the phase of a field. The phase of a field, so the speed of rotation of a field that is inside this delta term. And so during this time, we still have an evolution in the Bloch sphere. The Rabi vector will be pointing to the south pole or the north pole according to the sign of delta. And so the Bloch vector that was left on the equator after the first pulse will now start to rotate along the equator of the Bloch sphere. So this rotation happens at a difference of frequency delta. This difference of frequency delta is exactly the difference in the rotation frequency of a field with respect to the rotation of the atomic superposition. So this rotation of a Bloch vector around the equator of a Bloch sphere is basically what I was trying to explain you before when I said that a field is rotating at a different speed with respect to the atomic superposition. The difference is that now we are considering the same process, but in the rotating wave approximation, so where the only relevant frequency scale is the detuning. So we are basically subtracting the frequency omega from the resonance frequency. So now it is clear that depending on the final position of this Bloch vector after the rotation on the equator during the dead time, so the last pi half pulse could have different behaviors. Again, in the last pi half pulse, so this will be again, sorry, a Rabi vector on the equator. And so if you're, let's try to do things nicely. So if the final position in the free evolution was the blue one, so in this final okay, so I just realized that I'm sorry, I've just drawn things wrongly, so forgive me for that. And this happens, sorry. So this is V, and let's take U as orthogonal to the screen, otherwise this first rotation was not possible, of course. So let me now draw it properly. So this was the first case. I'm sorry for that. So let's draw the last pi half pulse more carefully. So this is U, and this is also the direction, of course, of omega. So now, if the state after the dead time was in this position, so the evolution of the last pi half pulse will bring the state to the excited state E, while if the final state of evolution was this state, so now the precession along the Rabi vector will bring this Bloch vector again to the G state. And so the effect of a second pi half pulse will depend on the time between the two pulses and on the detuning. So it will depend on the acquired phases. So in this sense, this is an interference effect between the first pulse and the second pulse. And you observe this quantum interference because you have coherence both in the field and in the atomic superposition. So finally, let's see it on the Mathematica example. So in the Mathematica example, I will simulate the whole Ramsey sequence. So in the first case, I will simulate the Ramsey sequence when you are on resonance. So when you are basically on the center of a central fringe. And so let's see what happens on the Bloch sphere. So this was the old result, so let me reset it. Okay. So this is the first pi half pulse. Then at that time, nothing happens. In the second time, for the second pulse, you have the pi half pulse, which complete the first pulse and produces a pi pulse. So during the central time, nothing is happening because the field is always in phase with the atom. And so in a rotating wave approximation, in the rotating wave frame, the two phases cancel. Instead, if you have some detuning now, and this will be very nice, and I hope that this will be useful for you to understanding Ramsey spectroscopy. So now you have the first pi half pulse. Then during the dead time you have an evolution because you have a detuning, and so you have a Rabi vector that is different from zero. So in other words, you have a running phase between the field and the atom, and if the acquired phase is equal to pi at the end of a dead time, so you see that you have a almost perfect destructive interference, and so the final state will be very close to G. Not precisely G, because as you can see here, you have some detuning, and so in the pi half pulse, the Rabi vector is pointing a little bit downwards. So this is the first minimum of a fringe of the Ramsey spectrum, and I will show you again in a moment. Finally, the last case is what happens on the first revival of Ramsey signal. So this happens at finite detuning when the difference in phase acquired during the dead time is equal to 2 pi. And so what happens here? First pi half pulse, then dephasing, but this dephasing will lead to a rephasing after a full circle of equator, and so the second pulse will lead to a constructive interference, and again, this is not perfect because you have some detuning. Now you're not on the central fringe, but on the first fringe, and so you will have a large population of excited state. Okay, so I hope that these examples could have interested you, and these are some examples in which we have not made any calculation of Bloch dynamics or Ramsey dynamics. So this is just based on intuition and representation of the Bloch sphere. That is something very useful for many applications, both in quantum optics, quantum information science, and also for the topics that we will discuss in the next weeks. So I think I have concluded this part on the review of atom-light interaction. And of course, I would be very glad of answering to your questions when we will meet again after this emergency situation has passed. For the time being, thank you for watching and see you soon.